Our next speaker is Professor Bernhard Schölkopf. Professor Schölkopf is one of the leading AI scientists in the world. He has made a lasting contribution to artificial intelligence by working on the support vector machines. He is currently director at the Max Planck Institute of Intelligent Systems in Tübingen. And despite being a public figure, he is also a dedicated researcher. He spends a lot of time and energy on a project very dear to his heart, and that is building the Cyber Valley as a competitive ecosystem for advancing applied AI research and integrating that research into industrial applications. Bernhard, Professor Schölkopf, we are very happy to have you here with us. Thank you very much.
Thank you very much. It's a great honor to speak today in this opening session, BitCon. And the session, of course, contains a range of impressive names. And I have the schedule over here, including, of course, the very special name, the most illustrious of all, and that's, of course, Harry Seldon up here. Now, unfortunately, Harry Seldon doesn't speak in person today, but that's actually a rather typical for him. For those of you who know Harry Seldon, of course, he only makes one live appearance early in the first book of Isaac Asimov's Foundation series. But at the same time, he's probably the single main character of the whole series. Now, who was Harry Seldon? Harry Seldon brought the science of psychohistory to its full development. The individual human being is unpredictable, he said, but the reaction of human mobs, as he called it at the time, Seldon found could be treated statistically. And this was published in 1951, this book. And I believe Asimov did not know at that time whether this science would ever exist. Now, if he read the New York Times, which is entirely possible because he grew up in New York, he may have seen this article, which appeared 7 years later, reporting on a new machine called the Perceptron. So Frank Rosenblatt depicted here demonstrated that the Perceptron learns from experience, and he predicted that later perceptrons will be able to recognize people or instantly translate language. And this was the birth of machine learning. Now, around the same time, there was another equally revolutionary development. And this was that people understood that computers can do more than compute numbers. They can process symbols. And this was really the birth of computer science as we know it. And there was optimism that the manipulation of such symbols in programs written by humans would actually be enough to generate artificial intelligence. And there was impressive progress early on seemingly hard problems such as computer chess. And Herb Simon, one of the fathers of the field, he predicted that machines would soon be capable of doing any work a human can do. However, it turned out that people's problems that appeared simple, such as most things animals can do, turned out to be rather hard. And this came to be known as Moaviks Paradox. So unfortunately, hopes were disappointed and interests, while computer science as a field was thriving, interest in AI eventually declined. And things were quiet for a decade or two until at some point suddenly the field of machine learning started to boom. And using machine learning, this is a video from my lab, using machine learning, we could suddenly start tackling those problems that look simple, but are really actually quite hard. Another impressive success of the learning approach was, of course, DeepMind and its Atari system playing a number of different computer games. And this was published in Nature, one of the first machine learning papers to appear in Nature. And this was at the time interpreted as a form or sold as a form of general AI, but I want to really qualify this. So the system is retrained on every single game from scratch. The training sets are huge. And the AI problem, and that's the most crucial thing, is effectively turned into a large-scale pattern recognition task with IID data. IID stands for independent and identically distributed. So nothing changes between training and test. And I've discussed this in a commentary that appeared in the same issue of Nature alongside this paper. So a real-world problem where progress has been rather impressive is object recognition. So we can train systems on huge sets of labeled images. And then by some measure of success, we can achieve human level accuracy. For instance, we can reliably recognize these cars and these images. But if there are things in a test image, such as a beach or the sea, that may be negatively correlated with the presence of cows in the training set, then the systems may not recognize those cows anymore, or do not recognize them anymore. And the reason is that machine learning really only looks for correlations. It doesn't care about causality. And it turns out that our systems are so highly optimized to a given training set that they're not robust even to tiny violations of this so-called IIT assumption. So if we add a little bit of malicious noise to a test image, imperceptible to a human, that this looks the same as this, then a system may suddenly classify a little pig as an airplane. So to get more robust, machine learning should move beyond statistics and incorporate causal knowledge. And the first person to understand the connection between statistics and causality was probably Hans Reichenbach. He postulated that if we find two variables to be correlated, then there must be a third variable that causes this correlation. And this third variable could coincide with one of the two. So for instance, if we find that the human birth rate and the frequency of storks are correlated, which is the case in European countries, then it could be that the storks bring the babies, it could be that the babies attract the storks, or it could be that something else, for instance, economic development, has a causal influence on both of these quantities. And another hard thing is these three situations are difficult to tease apart if you have only observational data. So you need something in addition to distinguish these cases. And much of our own work on causality over the last 10 years is based on an independence assumption, which I think humans also use. So I like to visualize it using this object here called a Boucher chair. So when we see this object, then our brain assumes that the object and the mechanism by which the light reaches our brain are independent. And our perception builds on this, because if we violate this assumption, for instance, by looking at the object through this little hole, so from a very specific point, then perception fails and we see a 3D structure that doesn't exist. So this principle can be phrased mathematically and used for learning causal structures from data. And we're trying to use this principle to train, currently to train deep learning systems that automatically learn causal variables from high-dimensional data, and that then allow meaningful manipulations of the learned representation. So for instance, in this case here, we might have a real object, a koala bear, another real object, a teddy bear, and then we have a completely synthetic object that we get by manipulating these representations, which looks a little bit like a koala teddy bear, I would say. So this is another example of causality in data analysis. It's a more recent one, which is about Simpsons Paradox. And this started with an Italian PhD student of mine, Luigi Resele, who started when the COVID pandemic began. He started to look at data and noticed that early on in the pandemic, the case fatality rates in Italy were actually higher than in China. And this puzzled him. His father is a doctor in Italy, and Luigi felt that the Italian healthcare system should be more capable than the Chinese one. But then as he dug into the details, he noticed that within every age group that he considered, it was the other way around. So overall, higher fatality rates in Italy, but in every age group, the other way around. And this is actually a textbook example, if you want, of Simpsons Paradox. And the reason for this, of course, is that the demographic is very different. So people in China are much younger than in Italy. And therefore, even though in each age group, people are more likely to survive in Italy, at least at that time, since the younger age groups are overrepresented in China, the weighted average by the age distribution turns out to be the opposite. And you can tease these things apart if you make a causal model. So you can tease apart the contributions from age, the contributions from country, and to try to understand the different healthcare systems, for instance. And if you look at that, it's interesting. You can even see the development in Italy. Initially, the effect of being in Italy was positive, so you're less likely to die. But then as the healthcare system got overloaded, this was actually turning around. So so we've applied similar kinds of methods in a range of domains, and from remote sensing to astronomy. And astronomy is maybe my favorite example. So that we used causal machine learning to remove the influence of instrument errors on signals that were measured using this Kepler space telescope. And using this, we discovered a range of new exoplanets, which was already fun. But then things got even more fun because with one of them we were very lucky, since it was subsequently discovered that by others, astronomers, this was the first exoplanet that is in the habitable zone around its host star, and at the same time, its atmosphere provably contained water. So this was a big thing at the time. So we've, in this very short overview, seen that AI moved from a symbolic stage, beginning towards machine learning, and now maybe it's starting to move towards a causal stage, which I expect will lead to more robust methods that allow better transfer from one problem to the next, that limit our dependence on huge training sets, and that are also predictive under interventions, and that hopefully will lead to more understandable solutions in some cases too. So let's look a little bit at the big picture. So the first industrial revolution, as we all know, was triggered by the steam engine, water power. Second one was driven by electrification. So both of them were about how to generate and convert forms of energy. Now, the current change has been called the digital revolution, but really it started already in the mid-20th century under the name of cybernetics, and it replaced energy by information. So like energy, information can be processed by people, but to do it at an industrial scale, we need, of course, computers. And like the industrial revolutions, we probably have two phases. The first one was driven by computers, the development of programming languages. The second one now unlocks a new information source by extracting information also from unstructured and real-world data. So, and the enabling technology for this is machine learning. Now, how is Europe doing in machine learning? Unfortunately, it's not great. So certainly America in terms of, so this is a statistics in terms of some of the top conference, America is way ahead. China used to be behind many European countries, but China is catching up fast. So it's clear no single country will be able to compete with those in Europe. Now, to address this issue, which is probably going to increase this issue, we founded the new Max Planck Institute 10 years ago. And this institute then gave a strong push to other local institutions in the area. And by now, if we count the whole site, so MPI and the universities, we are already among the top 10 academic research sites in machine learning, according to this statistic here. And this nucleus of academic excellence met a strong need in the regional industry, especially the car industry. And then government, as a consequence, government and industry pooled funding to build an ecosystem called Cyber Valley. And this includes a number of components: a new doctoral school, new professorships, new research groups, support for startups, a new model for industry collaboration, and so on. And importantly, all of this is transparently embedded into the public discourse. So we don't want to just duplicate the style of American or Chinese AI, but we want to build a distinctively European brand of AI. And we started with this regional ecosystem, but soon we learned that we can actually attract better people if we work together with other sites. So this applies in Germany. It applies initially with a few European partners where we had joint PhD programs. And it now applies with a whole set of partners in a system called ELIS. And I want to say a little bit more in the next few minutes about that. So this is a high-level plan how to make Europe competitive in this field. And it's based on three components. The first one is about excellence. So we know AI is extremely exciting, especially for young talents. And these talents that are now pushing into this field, they want to work with the best and they compare internationally. And many of those people will turn into future leaders themselves. So we better try to keep them here or get our share of them. The second point is about creating ecosystems, because our graduates nowadays don't pick the places only by academic strength, but they expect academia, startups. they expect academia, startups, and industry labs. And the third point is how to make each ecosystem stronger by joining forces. So we are working on 3 pillars. The first one are research programs. The second one is young talent, and the third one are sites, so research programs. Each of these programs is dedicated to a topic of current AI, and it brings together around 10 to 20 fellows, top people in Europe. And they range from basic research to application areas of machine learning, for instance, health or robotics. And their programs were initially reviewed by Joshua Bengio, the Canadian Turing Prize winner. And as a result, the fellows in these programs are really among the most highly cited researchers and leaders of the field. The second component is about attracting young talent. And here the most notable component is a PhD program. It's a meta program. It doesn't award degrees, but it brings together universities and LS members that co-supervise a student. And there's a mobility component, exchange visits, and we just launched it in the first call. We already had more than 1,300 applications, and I can say many of them truly outstanding. For many of them, this was the only place in Europe where they applied. So people are observing this, and we hope that we will turn into the #1 brand in Europe. So both these first 2 pillars, they are supported by a proposal which was successful in a recent EU call, and it received the top score among all of the proposals. So this was also a good thing. And finally, maybe the most important thing is we're working towards building LS sites and ultimately institutes. So in late 2019, we published a call for LS units. And by then we thought that LS would start developing a bit of a reputation, and we might maybe get 5 or 10 applications. But what we received actually blew us away. And by now, after 2 calls, we have 30 LS units in 14 countries. And they bring their own funding. So that it's a grassroots funding that comes from these units. They even commit funding to network activities. It's quite remarkable that as a result of this open call, 15 of the top 20 AI departments by this independent statistics in Europe have already launched LS units with their own funding. So these places include Cambridge, Oxford, ETH Zurich, EPFL, IST Austria, Max Planck, etc. So all these places are top-notch already, but they bought into this vision that they can be stronger by working together. And so within these 3 years since we started, LS has gained real momentum. And by now we've had, we started as a grassroots thing, but now we've had also a number of meetings, both with Angela Merkel, Margrethe Vestager, and working with a range of companies and other public institutions. And also in Tübingen, we're trying not to rest on what we've achieved until now, but we're now working on a new type of research site, which is going to be a kind of a public-private partnership, which incorporates a generous donation of 100 million euros from Hans-Werner Hector, one of the founders of SAP, and combines this, plans to turn this into an LS Institute and combines it with a Tübingen AI Center, which is part of the federal AI strategy, a competence center. And so maybe just to summarize or conclude, so as scientists, we clearly want to do everything and contribute our part to make Europe competitive in modern AI. And I would really like to appeal to you as industry leaders. I assume there are many industry leaders here in this audience to contribute to your part and also to help convince your governments to do the same, because we're all in this together and the future of Europe will depend on it. Thank you very much.
Thank you very much, Bernhard. So my apologies to other speakers. Honestly, that was my personal highlight today because not only what you said, which was really great, but you also know Harry Seldon. I'm so hyped, honestly, that there is someone else who knows Harry Seldon. But staying maybe with Asimov, we have maybe time for one question. Staying with Asimov is, of course, famous for the Foundation series, but also for his short robot stories. What do you think? When are we going to have Daniel, the human-like humanoid robot?
Yes, it's a difficult question. I think if we had talked about AI 10 or 20 years ago, we would have all thought of robots walking around and behaving like humans. And now much of AI has happened, and we don't see many robots walking around, surprisingly. So somehow it seems to be the case that the virtual world has increased in importance, and AI is mostly happening in the virtual world so far. But having said that, I think it's also going to arrive in the human world, and I would expect in the next 20 years we will see some of these things happening. Yes.
I can't wait, honestly. I think as AI has matured over the last 65 years, I think it lost also its ability to dream big. And I hope we'll have this kind of big dreams and inspirations coming back to us. So thank you very much for your time for this great keynote.